All right, welcome chemistry class. We are looking at chapter 13, review questions, and we're going to spend a little time together here going over these concepts in chapter 13 so you can understand how to answer these and also how to do some of the calculations and some of the different things that are found in this chapter. So let's dive into this and work together on getting some of these questions done, okay? All right, the first question here, number 1, says, how many moles of ions are contained in 1 liter of a 1 molar solution of the following compounds? Well, notice here we have 1 capital M, that's molar, that's molarity. And if you remember, molarity is moles of the solute divided by liters of the solution. Okay? So notice what we have here. We have 1 liter, that is the denominator. We have the concentration, 1 molar, that's this value right here, that's the actual concentration, and we should be able to find the number of moles of the solute. So all I'm going to do is I'm going to put in 1 for the M, and I'm going to put in 1 for the liters, and obviously, if I'm solving for the number of moles here, number of moles has to be 1. I have 1 mole of solute. But you have to be careful. Listen, it's asking for the moles of ions. What this number here, this is telling me I have 1 mole of the solute, which is the compound that I am trying to dissolve. So I have 1 mole of KCl. But KCl, when that breaks into its ions, when it's dissolved, it dissociates in water. So 1 mole of KCl, potassium chloride, is going to break apart into its ions, potassium cation and the chloride anion. So you get 2 ions for every 1 unit of that ionic compound. So for 1 mole of the compound, I get 1 of each of these for a total of 2 moles. So the answer here for A is actually 2 moles of ions. You get a cation and an anion from this 1 ionic compound. Okay? Let's go to this one. Magnesium nitrate, again, if I have a mole of the compound, this is going to break apart into what? Magnesium ion, which is a 2 plus, and notice this 2 right here, 2 of these polyatomic ions. That's a polyatomic ion nitrate. So you can get 2 of those. That's a charge of -1. But you get 1 magnesium ion and 2 nitrate ions out of every 1 unit of that ionic compound. So I get 1 plus 2, I get a total of 3 ions for every 1 unit of the compound. So if I have 1 mole of the compound, I'm going to get 3 moles of ions. This answer is going to be 3 moles. Okay? All right, next thing, it says use the solubility guidelines, and you can always refer to the guidelines when you're taking a test or doing your work. We're going to refer to those guidelines and predict whether these compounds are soluble or insoluble. Okay? So the solubility guidelines are, let me pull them up here, I think I have them. Yep, there we go. Solubility guidelines tell us when something is soluble or insoluble. Okay? So all I do is I look at what is given. Here, this compound is ammonium sulfide. So let's refer to the solubility rules. What does it say about ammonium compounds? Look at number 1. Right here it says ammonium compounds are soluble. Ammonium compounds are soluble. So we know anything that has ammonium in it is going to be soluble. Okay? Let's look at this one. And here it says lead chloride, and it specifies in cold water. Let's see if it says anything about lead chloride. Okay, it says here, it says number 3, most chlorides are soluble, which is what we have. We have a lead chloride. okay? And it says except, and it gives some exceptions. So the exceptions are silver, mercury, and lead. It says lead chloride is soluble only if it's hot water. But this says cold water, so this would be insoluble. Okay, insoluble. Let's look at C. What does C say? C says, and this is iron sulfide. Well, it says in number 6, most sulfides are insoluble. Insoluble. There are some exceptions, but this is not one of them, so this is going to be insoluble. It has a sulfide right there. That S tells us it's a sulfide, and one of the rules was sulfides are insoluble except, and it gives a few exceptions. But iron sulfide is not one of them. D, aluminum sulfate. What does it say about sulfates? Let's see. Sulfates, most sulfates are soluble, and it gives a few exceptions. Barium, strontium, lead, calcium, and mercury, but we have aluminum, so we're good, and it is soluble. Okay? All right, number 3. What is a net ionic equation? Well, let's just pull up the answers here for a second, and we'll look at that. A net ionic equation simply says what? And we'll abbreviate this. We'll summarize this, okay? It's basically, it's the equation that what is going to show the compounds and ions that are involved in the chemical change. If something is in the equation but it's not involved in the chemical change, producing something new, we get rid of it. Those are called spectator ions, okay? In order to come up with a net ionic equation. So this is the equation that only is showing the compounds and ions involved in the chemical change in an aqueous solution. Okay, you can write that down right here. Number 4, what determines the strength of a solute of an electrolyte? Well, the more ions we have, the more the ion or the ionic compound dissociates. So the more it dissociates, the more ions you're going to have, and therefore it's going to be a stronger electrolyte. Okay? Strong electrolyte is going to have lots of ions that dissociated very, very, very well. Okay? It says the strength of the solute is determined by the extent to which the compounds form ions, right there. Okay? How much does it dissociate? How much does it dissociate? Dissociates more, then it is a strong electrolyte. Remember, an electrolyte is going to conduct electricity. That's how we measure to be an electrolyte. Number 5 says distinguish between the use of the terms strong and weak and the use of the terms dilute and concentrated. Okay, well, strong and weak usually refer to how much something dissociates into ions. All right, and dilute and concentrated, these refer to the amount dissolved. Okay, but remember, you can have sugar dissolves, but it doesn't dissociate. Ionic compounds dissociate. Okay, let's just check and see what this is saying here. Yep, strong and weak refer to the extent to which a solute dissociated or ionized. How many ions do we have? Strong or weak is going to measure how well it conducts electricity, or how many ions. What's the strength of the ions in there? How well did it break apart into ions? Dilute and concentrated refer to the amount, the quantity of solute that is dissolved. Okay? All right, number 6. How does the presence of a non-volatile solute affect each of the following properties of the solvent in which the solute is dissolved? So let's look at, let's say I have a beaker of water. All right, that's water right there. But then I'm going to put something in it. I'm going to put some sugar in there. Okay? Well, when I start putting sugar in there, here are some sugar molecules that are dissolved. those sugar molecules are going to get surrounded by water. So these are surrounded by water, surrounded by water, surrounded by water, surrounded by water, okay? Surrounded by water. All of those sugar molecules are going to get surrounded by water. Well, how is that going to affect the vapor pressure? Vapor pressure is a result of what? The water molecules evaporating above the liquid. You're going to have gas particles, water vapor up here. Well, if these water molecules are busy, they're busy surrounding the sugar molecules, they're going to be attached, kind of attracted to these sugar molecules, they're not going to be able to evaporate as much. And you're going to have fewer gas particles, fewer water vapor particles above the liquid when you add a solute. So the vapor pressure will go down. It'll be lower as a result of adding the sugar. What about freezing point? Freezing point is going to depress or lower the freezing point of this now sugar solution. So that also will go lower. Freezing point depression. Freezing point depression. Okay? Boiling point, you're going to have to heat this up even higher in order for it to boil. The boiling point is going to go up. It's going to be higher as a result of adding a solute. Okay? And the osmotic pressure is going to be greater, I believe. Okay? Osmotic pressure, remember, is the push that you have to give in order to keep the water from going through that semi-permeable membrane into the sugar solution. All right? So the greater the concentration, the more that water is going to want to come over from the pure water side into the sugar side, and you're going to have a higher pressure to push it back. Okay? Let's double check. Okay? Lowers the vapor pressure, lowers the freezing point, raises the boiling point, and increases the osmotic pressure. Okay? Number 7. What is the relationship between the freezing point depression, we use that symbol right there, for a solution with X concentration of solute and one with 2X? Well, here's the formula. Just look at the formula. Here it is. Delta T sub F, that is the change in the freezing point temperature, is equal to some constant times molality. So if this number right here doubles, if that doubles, what's going to happen to this number? It also is going to double. It is a direct relationship. This is your constant. That's not changing. Okay? The concentration can change. If you double it, that would double the freezing point depression. That would double how much the freezing point goes down by. Okay? Number 8, why does the level of the more concentrated solution rise when two solutions are separated by a semi-permeable membrane? All right, great question. So here is my semi-permeable membrane. Over here we've got pure water. And on this side we have a sugar solution, sugar water. All right, so over here we have pure water, H2O, H2O. But over here we have sugar, and those sugar molecules are surrounded by H2O molecules. Okay, so I'm going to keep this real simple. Let's say we only have 4 water molecules on this side, and they're all surrounding the sugar. Over here we have 4 water molecules as well. Okay, what the effect here is that these sugar, this sugar molecule is being attracted to all the water molecules, and this is no longer pure water. You have just reduced the concentration of pure water over here. Now it is a sugar molecule surrounded by water, and over here you've got 4 pure water molecules. Now on this side, the sugar side, you've got 0 pure water molecules. 0, because they're all surrounding around the sugar. That's not pure water. So what happens is they want to balance it out. So let's imagine, to balance it out, these 2 water molecules come over here in order to balance out the pure water molecules. So those 2 go over there. Now you've got 2 on this side and 2 pure waters on that side. Okay? So it's trying to balance out the pure water molecules. You've got too many on this side compared to the side where there's a solute, because these water molecules are kind of attracted to the sugar, and that's not a pure water molecule anymore. So they kind of think of it like, hey, these water molecules on the pure side are coming over to help the water on the sugar side to dissolve that sugar. It needs some help. Okay? So the more concentrated solution, the level of more concentrated solution rise. So as you add more, as you have this semi-permeable membrane, more and more water is going to come on this side, and the solution level is going to go up over here. It's going to get more and more of the water coming on that side. That's why the level of that solution is going to go up. Okay? Number 9. Write the equation for the dissolution of each of the following ionic compounds in water. Okay, so all you're going to do is you're going to recognize that this is an ionic compound, metal and nonmetal, and it's going to break apart into its ions. So this is going to break apart into magnesium and chloride. What's the charge on magnesium? Magnesium is in group 2, so it's going to have a group 2 metal ion charge, which is always a +2. Chloride is in group 17, non-metal, and that is always a -1. But notice right here, in the compound, there are 2 chlorines for every 1 magnesium. So when they all separate, you don't put the subscript 2, you put a 2 in front to show there are 2 separate chloride ions that are now separated, and the magnesium ion. So you get, for this 1 unit of magnesium chloride, you get 1 and then 2 more ions. You get 1 magnesium ion and 2 chloride ions for a total of 3 ions in that 1 unit. That's how it dissociates. Okay? Notice it's balanced also is what I'm doing. I'm really balancing it. Okay, I've got 2 chlorine atoms in this compound, so I have to have 2 on this side as well, showing though that they're separate by having a coefficient instead of a subscript. The subscript is only if they're bonded together. All right, let's do this one. I have a metal and I have a polyatomic ion. The SO4 is an ion that's stuck together. That's a polyatomic ion. The S and the 4 oxygens are going to stay together as a single ion. You have to know that. So this is going to break apart into sodium, which is a +1. It's in group 1. And the SO4, you just look it up on the chart, is a 2-. That's why there's 2 sodiums. So I need to balance this. I need 2 sodiums to be balanced on both sides. So for this sodium sulfate here, sodium sulfate, that ionic compound, you get 2 sodium ions and 1 sulfate polyatomic ion when it dissociates. All right, let's look at the number 10. Number 10 here says write balanced chemical equation and the net for the reaction. Okay, aqueous mercury 2 chloride and aqueous potassium sulfate. So let's write these 2 down. Mercury 2 chloride. So mercury, Hg, mercury 2 means it has a +2 charge. Chloride is a -1. So I'm going to need 2 chlorides to match the 1 mercury 2. Plus, and this is aqueous, Aq, potassium sulfide. Potassium is a +1. It's in group 1. Sulfur forms the -2 sulfide. It's in the same group as oxygen. And so this is going to be K2S. I need 2 Ks, each is +1, to match the -2 on the single sulfide. This is also dissolved in water. Then, what's going to happen? If we mix all of these together, now all 4 ions can interact. So right now, in this solution number 1 over here, we have the mercury and the chloride ions dissociated. I know I put them together in a compound, but when it says aqueous, it means they're dissolved in water. We know that they're going to dissociate into ions. And in solution number 2, I have this metal, potassium, and with the sulfide ion, and they are dissociated in solution number 2. Now when we mix them together, now this mercury can also interact with the sulfide. This metal mercury from solution 1 can interact with the non-metal from solution 2. And this potassium can interact with the chloride from solution 1. So potentially we could form potassium chloride. That's the formula for potassium chloride, because potassium is a +1 ion, Chloride is a -1, just need one of each. And the other potential new compound is mercury 2 sulfide. Mercury 2 is a +2, sulfide is a -2, so you just need one each of those. And if we look at our solubility table, let's check. Are either of these insoluble? Yep, sulfide. Sulfide is insoluble. Over here, it was not insoluble. It's soluble because it's with the potassium. Potassium is soluble, potassium compounds. But now that it's with the mercury, it is insoluble. So this is going to be a solid, and this is still going to stay dissolved. Potassium chloride is soluble. And this is our balanced chemical equation. Oh, I got to balance it. Notice I've got 2 chlorides on this side, 2 potassiums on the left side. All I have to do is put a 2 in front of that, and now it's balanced. Okay? Now, let's take this a little step further. Let's break this apart into ions. Anything that says AQ, I'm going to break it apart into its ions. Watch. Hg plus 2 Cl, this is Hg2 plus, and the Cl negative, there are 2 of those, plus 2 potassium ions, plus 1 each, and the 1 sulfide, which is a -2. And that breaks apart into, this breaks apart, but you're going to get double, you get 2 of those, so 2 potassium and 2 chloride. And this guy does not break apart. That's a solid. HGS mercury 2 sulfide is a solid. Okay? Now let's get rid of anything that is not reacting, is not forming anything new. Notice potassium on this side, potassium on that side. And chloride ion on this side, chloride ion on that side. They're the same on both sides. What is different is Hg2 plus, let's see, I'll write it up here. Hg2 plus and the sulfide 2 negative, these are from separate solutions originally, they came together when we mixed them to form what? The mercury 2 sulfide precipitate. Okay? There you go. This is your net. This is the net ionic equation. All right, what precipitate, if any, forms when aqueous copper 2 chloride, that's aqueous, so that's dissolved, that dissociates, reacts with aqueous ammonium phosphate. This is aqueous as well, so those are dissociated. But when we mix them, the metal from here could combine with the non-metal from there, from the other one. And the chloride could combine with the ammonium. Well, we just check our solubility rules, and if we do, we will see that ammonium, according to rule 1, is always soluble. So I know ammonium chloride is going to be soluble. But what about the other one? Phosphate. Let's look at the rules for phosphate. Phosphates, right here, insoluble. Insoluble. There are some exceptions, but those exceptions don't apply here. So copper 2 phosphate is going to be our insoluble precipitate. Okay? Copper 2 phosphate. Identify the spectator ions in the reaction between KCl and AgN. Okay, here, let's go KCl plus AgNO3. Let's go ahead and write this out. This is going to break apart. This is going to be soluble, potassium chloride according to one of the rules, and silver nitrate. What does it say about silver nitrate? Let's see. Nitrates are soluble. So silver nitrate is soluble. These are both going to be soluble. Okay, but when we put them together, now the potassium, the metal from here, could form a compound with the non-metal from over there. It could have potassium nitrate. But I know anything that has potassium in it is going to be soluble. That's AQ, that's aqueous. What about silver chloride? The metal from the second one and the non-metal from the first one. Silver chloride. What does that do? Let's check our solubility table. Most chlorides are soluble except, there it is, except silver. Silver is not soluble. So this is going to be your solid, which means the potassium over here was dissociated, and the nitrate was dissociated, and there's still AQ here. So this potassium is going to be an ion, this potassium is going to be an ion, that nitrate is going to be an ion, just like it is on this side. Those are your spectator ions. So your spectator ions are what? The potassium ion and the nitrate ion. Those are not involved in forming the solid, the silver chloride. Okay? All right, 13. Copper 2 chloride. Copper 2 chloride, here's the formula for copper 2 chloride, and lead 2 nitrate. So lead 2 nitrate, there's the formula for lead 2 nitrate, react. Those are both aqueous, so these are already dissolved and dissociated. We're going to write the balanced chemical equation, the overall ionic equation, and the net. Okay? So watch. Here we go. Now we're going to mix these two solutions together. What's the new possibilities? The metal from here could join the non-metal from the other solution. So we could have copper 2 nitrate. Copper 2 nitrate. Just like that. And the metal from the second one, the lead, could join the non-metal from the first one. Lead chloride. Just like that. Okay? Let's balance it. I got 2 chlorides on both sides. I've got 2 nitrates. Yep, everything's balanced, so we're good. Now, let's see if we break apart into ions. Does everything break apart into ions? Does everything dissociate? Well, we're told that this is aqueous. We're told that this is aqueous. So we know that that is going to form the ions. And we have to look at our solubility table now. This has nitrate in it. What do we know about nitrates? Nitrates are soluble. So that means this is going to break apart into ions. What do we know about chloride? See, it has a chloride in it. Chloride are soluble except if it has lead, and it does. So we're going to assume it's insoluble because lead chloride is only soluble in hot water. So we're going to assume that this is insoluble here. So lead chloride is not soluble. We're going to put an S there. Okay? So that is the overall ionic equation. Now we're going to cross out the things that appear both the same on both sides. So the copper ion, the nitrate ion, and that leaves us with what actually is forming the precipitate. What is actually doing the chemical reaction here? And there you have it. That is your net ionic equation, the last line. Okay? Oh, and there's a follow-up question here. It says, if 13.45 grams of copper 2 chloride, that's this guy, copper 2 chloride, react, what is the maximum amount of precipitate that could be formed? This is where we have to do a little stoichiometry. Now, in our balanced equation, it is a 1-to-1 reaction. It's a 1-to-1 ratio for our copper 2 chloride and the precipitate of lead chloride. So however many moles of copper 2 chloride I have, that's exactly the same number of moles of lead chloride. So let's just find out how many moles this is. 13.45 grams of copper 2 chloride. Well, I have to look on the periodic table and I have to find the molar mass of copper, and then you have to add that to the molar mass of 2 chlorides. Alright, so you're going to look on the periodic table. I don't have to do this for you. Look on the periodic table, take the molar mass of copper, add it to 2 times the molar mass of chlorine, and you are simply going to divide by that number, because 1 mole is going to be that mass right there, the molar mass of copper 2 chloride. So whatever value this is right here, that's going to go in there, and you're taking 13.45, divide by that number, and that is the number of moles of copper 2 chloride. And that's going to be exactly the same number of moles as our precipitate because they're in a 1-to-1 ratio. Okay? Same number for both. All right? So I'll let you do that. 14. How many grams of antifreeze, and there's the formula for antifreeze, would be required per 50 grams of water to prevent the water from freezing at a temperature of negative 20 degrees Celsius? Okay. So what we're doing here is we're trying to lower the freezing point. Trying to lower the freezing point of water down to negative 20 degrees Celsius. That's a drop of 20. Normally water freezes at 0. But we're going to drop it down so that it has to freeze, has to get to negative 20 to freeze. That keeps the solution in your radiator from freezing. You don't want that solution to freeze, okay, in your car. So here's your formula. Delta T sub F, that is the freezing point depression, is equal to K sub F times the molality, All right? Now, this number here, the delta T, is actually given to us. We want it to drop 20 degrees. So this is actually 20, or I guess it'd be negative 20, right? Negative 20. This K sub F is a constant. This is for water. I believe it's negative 1.86. I could be wrong. We can look that up. And then this M here is our molality. So all you're going to do is this. You're going to take and solve for your molality. Divide both sides by negative 1.86. All right. I'll just do that really quickly. .75 about, okay, 10.75. Now, that's not your answer. It's not asking for the molality. It's asking how many grams of this solute would be required per 50 grams of water. So now what we're saying is you have the molality. Molality is moles of solute divided by kilograms of the solvent, which is the water. So you have this number, we just got it right there, 10.75, and we have the kilograms of water. We have 500 grams. 500 grams is, divided by 1,000, that's going to be half a kilogram. Okay, move it over 3 places. So 0.5 here, okay? And that's going to give us the number of moles. So I'm going to multiply both sides by 0.5. And when I do that, this is going to be what? 5.3 whatever, okay? 5.375, okay? That's your number of moles. That's your number of moles. Now, you have to be careful here. It's not asking for the number of moles. It's asking for the mass, the grams. So now you have to take your moles and you've got to find the molar mass of this guy right here. I'm going to let you do that. Look on your periodic table, add up 2 carbons, 4 hydrogens. Look at the 2 here, 2 oxygens and 2 more hydrogens. Take that number and you're going to take your 5.375 moles times the molar mass that you find from the periodic table. That will give you the answer you're looking for. Okay? You need to finish that up. Okay, 15. It says pure benzene, and there's your formula, freezes at 5.45 degrees Celsius. This is what it normally freezes at. A solution containing 7.24 grams of this, it's a different thing, that's your solute, in 115 grams of benzene freezes at this. Notice it went down. So it's asking what is the molal freezing point constant for benzene. So again, all we're doing is using this formula. Okay? And it is telling you the original freezing point, but now it went down to this, so they're telling you the change. They're giving you the change by telling you the original and the new. So let's find out how much it went down by. 3.55 minus 5.45 will give you the depression, how much the freezing point went down by. Okay? And it says here, the solution contains 7.24 grams of your solute in 115 grams of benzene. This equals your K, and the molality, what is molality? It is the moles of the solute, this guy right here. So you've got to do 7.24 divided by the molar mass of this C2Cl4H2. 2 carbons, 4 chlorines, 2 hydrogens. Add those all up, that is going to be the molar mass right there. Take 7.24 divided by that. This is going to give you the number of moles. This here, this is going to give you the number of moles of this solute. Okay? Then you're going to divide by divide that by the kilograms of the solvent, which is the benzene. Change that to kilograms by dividing by 1,000, so it's 0.115 kilograms. Okay? So what do you have? You've got this number, you have this number, and you have this number right here, because you're going to find that molar mass, and you then have to find this K. This K is simply going to be this value right here, the difference, divided by this number right here, which is the molality. Okay? And you can do that. All right, number 16. Oops, sorry. Number 16. Determine the molality of a water solution that has the boiling point of 102.805. Okay, boiling point usually of water is 100 degrees Celsius. It went up higher. So it's similar formula, delta T boiling equals the constant times the molal. Okay? Let's look at the constant for the boiling point elevation of water. I kind of forgot that one, so let's look at that really quickly. Sorry, let's look at it here. Here we go, freezing and boiling. There it is. Alright, so it is 0.51. 0.51 right there. Okay? 0.51. So here we go. You have your change is the difference between 102.805 and 100. So it is going to be 2.805. It went up by a little over 2 degrees. And determine the molality. We know this K is 0.51, and you just have to find the molality. So the molality is simply going to be the 2.805 divided by the 0.51, and you're done. Okay? This is, by the way, in moles per kilogram. Moles per kilogram. Okay? 17. Determine the expected boiling point of a solution made by dissolving 25.0 grams of barium chloride in 0.150 kilograms of water. Okay, so this is your formula. Delta T for boiling, the change in the boiling point is equal to the constant times the molality. Expected new boiling point. And what we have here is our constant for boiling is 0.51. This number right here, 25, is your mass but you're going to have to divide that by the molar mass of barium chloride. So you got to look on your periodic table, take the molar mass of barium, and barium chloride, by the way, is BaCl2, so it's going to be 1 barium and 2 chlorine. From the periodic table, add those up, and that is this molar mass right here that you're going to divide 25 by. Okay? Here they're giving you the kilograms of water, 0.150, and all you got to do now is solve for this value. Take 0.51 times this molality. That's going to give you the elevation. And this is for water, so then you would take that and add it to 100. Okay? And that will give you the new boiling point of your solution. And the last question, we made it. Number 18, experimental data for a 1 molal magnesium iodide aqueous solution indicate an actual change in the freezing point of -4.78. Okay? Find the expected change in the freezing point of water, and then B, suggest a reason for the discrepancy between the experimental and the expected values. Okay, well, let's look at this here. If we take this here, we have 1 molal, and let's go ahead and find our expected change. This is for freezing, okay? And this is aqueous, so it's for water. So we're going to use the K value for water. And we are going to use the K value for water, which is -1.86 for freezing. And we are given the molal here of just 1. Okay? So we would expect the temperature to go down by 1.86. We would expect it to go from 0 down 1.86. So the new freezing point would be -1.86. But it's not. It is -4.78. Why is that? Well, your reason for that is because this is an ionic compound, and it breaks apart into the magnesium. Let's write this down. It breaks apart into what? Magnesium ion and 2 iodide ions. So actually for every one of these, you're going to get 1, 2, 3. You get 3 ions. It's actually triple the concentration of what you expected. So watch what happens if I take that into account. If I look at this formula and I say, oh, I have to think about how many ions are created from this 1 molal concentration. So yes, my constant is still the same, but here my molality has to be tripled depending on how many ions I have. Okay? So if I take this and I take my answer here and I multiply by 3, I'm going to get closer to the actual value of -4.78. May not be exact, but it's going to be closer. Okay? Alright, so that is the deal that's happening, is you have to think about how many actual particles are created. The 1 molal is measuring the concentration of the compound, but that compound breaks apart then into 3 ions, so actually there are 3 times as many particles as you would expect by just looking at the molal. And that's why the freezing point depression is actually lower than what we expected. That's the answer to B. Okay? Alright, ladies and gentlemen, that's conclusion of the review questions. I hope that was helpful. As always, let me know if you've got questions, and I will get back to you as soon as possible. Love to help you and love to make sure you're understanding everything. So let's keep working hard and keep up the good work.